So next talk is about formally verifiable generated ASN, ACN encoders and decoders, a case study. And Samuel Chassot will be the speaker.
Ready.
Okay, thank you for your introduction. And so I will present to you our work on the formal verification of serializers and deserializers in the context of space exploration. So to introduce our project, the motivation was that space exploration needs serializers because, of course, a spacecraft needs to communicate both with the ground and sometimes with other spacecraft, and data need to be serialized. However, writing by hand this kind of code is bug-prone and really hard and time-consuming. And as an example, I can give you the fact that the Solar Orbiter probe, which is currently around the Sun, had bugs in the serialization work. Different instruments were using different NDNS and different paddings, and so this had to be patched after the launch. And happily, this doesn't have an impact on the mission, but it's not always the case, and so correctness is critical because bugs could lead to either the loss of very important data or worse, of the entire spacecraft. And so one of the solutions is to generate the code to reduce this kind of problems. And so to do so, we can rely on formats such as ASN.1. So what is ASN.1? So ASN.1 stands for Abstract Syntax Notation 1, sorry. And it's a language to describe data structures for serialization. Closely related to ASN.1, we have a bunch of encodings that are describing how this data should be encoded at the binary level. So we have a bunch of them. And I will focus on ACN, which is a bit different because it allows the user to customize the binary encoding format. And this is particularly useful if you want to re-implement serializers for legacy formats, because you can customize to support this legacy format. Today, ASN.1 is widely used in telecommunications, notably for HTTPS certificates and in 5G protocols. And for ESA missions, they are using the ASN.1 SCC compiler, which is a compiler that takes a description in ASN.1 and generates the code for both encoding and decoding these messages. So now let me show you an example of an ASN.1 format. So here we have a message that is a sequence. So a sequence in the ASN.1 language is a record type. And so here we have an ID, which is of the type that is defined above. So we have integers, we did bounds for the flag as well. For the value, we have a real, which is a floating point number. And for the description, it's a string of 10 bytes. And so with this format, you can now add an ACN description that looks like this. And this description is actually explaining how the encoding should be performed. So here, for example, for the identifier type, which was an integer between the two bounds to be a 16-bit integers, we can specify the size in bits. We can specify that we want to use two's complement, and that you want to use little NDNS. And then for the message, let's say that we want to specify the flag, which, let me remind you, was between 1 and 255, should be encoded on 9 bits for legacy reason, that we want to use the positive integer encoding, and that we want this to be aligned at the next 32 bits. And for the floating point number, you can specify the IEEE norm like this. Okay, and now I will give you a background on the ASN.1 SCC, which is this compiler used by ESA missions. So it's a compiler for ASN.1 and ACN. Before our project, it was supporting C and ADA as backend. And the code that is generated is a combination of static primitives. Among them, we have a data structure, which is the bit stream, representing a bit stream. And we have basic encoders and decoders for the basic types, which are named codecs. And we have one codec per binary encoding. And it provides the building blocks for this generated code. And so our project was to add a verified Scala backend to this compiler. And so as we were performing formal verification, I will quickly give you an introduction on our tool that is called Stainless. So Stainless is a verification framework for Scala that we are developing in our lab at EPFL. And so let me start with an example of a proof. So let's take this zip implementation in Scala that takes a list of integers and a list of booleans and create the list of pairs recursively by zipping the content. And so now let's say we want to add some specification. So we can add a postcondition like this using ensuring. So ensuring is part of the Scala language, but in the original Scala, it's performing a runtime check. And here we are repurposing it for static verification. So this postcondition is saying that taking the first element of each pair is actually giving you back the first list you receive as argument. And if you pass that to stainless, we get this counterexample. And indeed, this postcondition is violated if the first list is shorter than the second list. And so to counteract this, we can add a precondition using require, which is also a static check, runtime check in Scala. And now if you pass this to stainless, it's able to prove the postcondition correctness and other properties such as termination. And so now let me give you an overview about how stainless works. So it starts with the source code and then uses the front end of the Scala compiler to get the abstract syntax tree. And then it extracts its own version of the AST from this .AST, which is the one given by the compiler. And then it's applying a bunch of tree transformation on this AST, which could both reject some programs that are unsupported or transform away some features. So for example, here we are transforming while loops into tail recursion. We are transforming imperative code into functional code. And we are also rejecting some programs that uses aliasing in a way that is not supported. Then this AST is passed to the verification condition generator. It's based on the type checking of system FR, which is a type system based on system F with refinement types. And this type checking will produce a bunch of proof obligations that are then passed to Inox, which is a subsystem of stainless that solves this condition on the Inox AST, which is a purely functional programs with higher order functions and different things like algebraic data types. And Inox is using SMT solvers and function unrolling to deal with recursion. And so function unrolling allows it to not use quantifiers in the SMT queries unless the user is specifying them. And it's better for performance and to find a counterexample like I showed you in the previous slide. OK, so now we can dive into this particular project. So I will present to you the verification approach that we followed. So we split the verification in two main steps. The first step was to prove the runtime safety of the code. And this includes the absence of crashes and the termination. If you want to have a look at the paper, this corresponds to levels 1, 2, and 3. At that stage, we had to make sure that the code was accepted by stainless because stainless accepts only a subset of Scala. And so we had to refactor the code to make sure that this was accepted. Then stainless generates a bunch of VCs automatically. And this includes the termination, the check for the inbound accesses to arrays, the absence of overflows, the absence of division by 0, and so on. And so at that stage, we wanted to make all these automatically generated verification conditions correct. And in particular, for the inbound accesses, we had to add specification to all functions to express how many bits they would write or read to make sure that we could prove that we stay within the bounds of the arrays. And then the step 2 was the semantic correctness. And in this project, we were interested in the invertibility property. And so we did that twice, once for the static primitives and once for the generated code. And this is what we will explore now. And so we'll start with the static primitives. So we will talk about the bitstream and the codec for the ACN format. So starting with the bitstream, so as the name suggests, it's a data structure to represent a stream of bits. And it's used for both encoding and decoding. It is implemented on a mutable array of bytes with a moving cursor that is represented by two variables, one to point to the current byte and one to point to the current bit. It offers plenty of operations to read and write, both at the bit and the byte level. And this is the entire list, so I won't go into much detail here, but you can have a look in the paper. But for example, we have very simple functions like append bit and read bit that are used to write and read one bit at a time. But we also have more complicated functions like this append bits MSB first that takes an array of bytes and write a given number of bits starting with the MSB. So for the verification, the step 0 was of course to implement this Scala version of the bitstream. And to do so, we translated it back from the C backend. And we wrote a bunch of test suites to make sure that this implementation was behaving in a similar way. Then the step 1, as I said, was proving the runtime safety. And so we did the refactoring. And to prove the inbound accesses, we added the specification for the number of bits written and read by each function. And let's have a look at an example. So this is the append bit MSB first. So for now, we will ignore the implementation, and we'll focus on the post condition. So here I omitted most of it, but I want to show you this particular one about the number of bits written. And so here you can see that we are comparing the bit index that we had before with the bit index that we have after. So the bit index is an index at a bit level computed out of the cursor. And here we want to prove that this bit index after is equal to the bit index we had before plus the number of bits we were supposed to write. And this proves that we indeed wrote n bits into the bit stream. And so we did that for all the functions. And then we could go into the step 2 of verification to prove the semantic correctness. So again, we wanted to prove the invertibility. That is, if you decode right after encoding something, you should get the same value back. So again, let's have a look at this example of append bit MSB first. So now we can quickly see the implementation. So it takes an array of bytes, a number of bits to write, and a from, which is the index to which we should start in this source buffer. And it is implemented in a loop that is here implemented as a tail recursive function that writes bit by bit, taking from the input array and writing to the bit stream. And the post condition here, again, I omitted part of it. So the line 4 is constructing a new bit stream instance based on the one we have after the call by just moving the cursor back to where it was before. And then we would read n bits from this new bit stream. So we would actually read the bits that we just wrote. And then we are comparing them with the input buffer that we received. And so here, please note that the read bits function returns an array of bytes, again, to represent the bits that we are reading. And this is important for the next step. So now let's discuss quickly the proof of this function. So it is done by induction. And so as I said, we are writing bit by bit into the bit stream. And so your induction hypothesis is that when you are writing bit I, you can assume that from bit I plus 1 to the end, this is invertible, and you have to prove your step for the bit I. But as the read function is returning an array of bytes, this makes applying this induction hypothesis tricky because reading from bit I plus 1 returns a completely different array because everything is shifted by 1. And so this makes applying this induction hypothesis tricky. This was not an issue for the safety because we did not prove anything about the contents, but only about the number of bits. And so the solution we found was to go through a list of bits. And so we re-implemented a read bit function that returns now a list of booleans instead of the array of bytes. And so now you can see that reading from bit I plus 1 gives you the tail of what you would get if you read from bit I. And so this makes applying the induction hypothesis really natural. And then we have to prove that if you have the same list of bits, then you get the same array of bytes at the end. And in a nutshell, this shows that inductive structures are indeed better suited to do inductive proof compared to arrays of bytes like in the original code. OK, so now let's discuss the ACN codec primitives. So the ACN codecs is structured in a similar way as the bit stream, so it also offers primitive encoding and decoding functions. For example, we have functions to encode and decode 64-bit integers within some interval. And so the verification follows the exact same approach. And it relies heavily on the correctness of the bit stream. So I want to point out now that we did not prove the correctness of the floating point numbers functions because Stainless does not support floating point numbers. And we did not prove the invertibility for string-related functions because they are very rarely used. So I won't go into more details about this proof because it's the same scheme as what we already saw. But I want to show you this trick that we used at some point because I think it's interesting. So this is an auxiliary function that happens to be in this codec. It's not very important to understand what it does, but it takes an unsigned integers and converts it to assigned integers by considering only some bytes. The important part is that at some point we have this loop. So again, the details are not very important. The important observation is that the number of iterations is bound by 7 here. And so to do the proof, we had to come up with a while invariant for this loop to prove the properties we needed. And this was really tricky and time-consuming. And so at some point, we thought, why just not unroll this loop entirely? Because we know that the number of iterations is quite small. And so we did. And now the proof was completely automatic because Stainless was able to reason about that and not about the while loop. And so this shows that sometimes it's easier to refactor your code rather than trying to prove it at all costs. OK, so to conclude about the static primitives, Let me give you a few statistics. So the bit stream is around 3,700 lines of code, proof and implementation, and the ratio is about 5 lines of proof for 1 line of code. And for the ACN codec, we have around 4,000 lines of code. I did not compute the ratio, but it's rather similar. Okay, so now we can discuss the generated code part, and specifically how we tailored the code generation for the verification. So again, the high-level idea of the proof is exactly the same because the code looks similar, just that now everything is generated, so we need to generate the proof automatically. And so we needed to tailor the generated code for the verification. So now I will show you two ways in which we did that. So one first observation is that in the original backends, decoding was using in-place mutation for decoding, which means that decoding functions would receive an empty buffer and they would decode the value and write into that buffer. But this was incompatible with the aliasing policy in stainless. And so we had to move to a more functional approach in which decoding functions return the decoded value. But now the question was, how should we treat sequence of? So sequence of in ASN.1 is an array of values. And so how should we treat them? Like, should we return an array that we allocate within the decoding function? Or should we append the decoded elements to some given collections? And so to answer this question, a really important observation is that sequence of could contain other sequence of as values. And so the problem we have at that point is that if you use arrays, you would have mutable arrays within other mutable arrays. And this, again, is incompatible with the aliasing policy that our tool supports. And so we had to find another way. And the solution we took was to replace the arrays by vectors. And so in the Scala world, a vector is an immutable collection that offers rather performant operations like the append, prepend, init, and tail is done in amortized constant time. And the random accesses, which I used in our project, are in O of log n. And this performance was acceptable for our use. And so then we used this instead of arrays, and we used lists to specify the content for the verification because list is better supported by our tool for now. And by the SMT solvers as well. Okay, so now we can discuss the verification itself. So again, we go through our steps. So first, runtime safety. So the approach is exactly the same. We again have to prove how many bits is written or read by each function. The crucial observation here is that now the size is unclear because we are generating the code. We can't really know in advance, like while writing the compiler, how many bits we would read or write per function. So we have to generate a size function at the same time. And so if I can show you this example. So here we have another message in ASN.1, which is a choice. So it could be either a sequence of 2 integers, so a record of 2 integers, or just an integer. And so now the size looks like this. And now you can see that when you decode a message of that type, you have to check whether you have the flag choice 1 in your bit stream. And if that's the case, the size is given by this formula. And otherwise, you have to check for choice 2, and it's given by this formula. And so the principle of proving the runtime safety is the same, but the proof was a bit more tricky because of that. And for the semantic correctness, again, the approach was similar. It was relying heavily on the bit stream and the codec proven properties. And the only main difference is that now the proof is generated. So we have to generate the specifications. We have to generate the lemmas to prove the specification. And we have to generate the lemma applications at the right place within the code. So that, and this was the main, our main objective, that everything verifies automatically without any human interaction after the code is generated. And so I won't go into more detail about this proof, but I invite you to read the paper if you're interested. We have more details there. So now I want to show you a few experimental results that we have. So we tried our system on different packet formats for the real world. So we tested on the PUSC services, which is a set of around 300 packet formats, and it stands for Packet Utilization Standard C. And it is the standard specification used by ESA satellites and ground control. And it is used nowadays in 2 missions that are currently in space, CAOPS, which is an exoplanet transit observation mission, and PROBA3 to demonstrate a tandem flight for satellites. And the other set of formats we used was TC packet, which is the telecom and packet formats for ESA to send commands to satellites. So we generated the code and we ran the verification on both the static primitives and all these packet formats generated code. And we ended up with this, so around 335,000 VCs generated in total. And I won't go into more details about this, but you have the entire distribution, the 3 columns, so you have the library, which is these static primitives, and you have the formats for PUSC services and for TC packets. And so I gave you this number so that you have an idea of the scale of this study, and so you know it's the largest verification project that we did with our tool to date with respect to the total number of VCs at least. Okay, and so to conclude, I will give you a few. Yeah.
What was U and I column?
So V is verified, U is unknown, and I is invalid, and so I can give you more detail about that maybe at the end of the talk.
That's okay.
So I will give you a few lessons. So first, we found some bugs within the existing backends. So I will give you a few details. So the first one we found was that the not a number bit pattern was incorrectly handled in the C and ADA backends. Specifically, some assertions would have failed. And so we found this bug while translating from C to Scala. Then we found that the alignment requirements of sequence, so this record type, was handled also wrongly in the C and ADA backends. And we also found that while translating C to Scala. Then we found that the choice pattern was wrongly decoded, specifically when the choice was optional and the flag given in an ACN format. And so we found this bug while writing the proof. And the last one was some missing validation checks for 7-bit strings that are encoded on 8 bits. And this bug was found by Stainless while running the verification. And so it's important to note that all these bugs are reproducible with Stainless. It's just that we happen to find them earlier in the pipeline, but you could also have found them at the end. And they are now fixed in all backends, so C, ADA, and Scala. And finally, I want to give you this takeaway that we learned during this project, is that every step counts in this process. So as we were verifying some existing code, we had to perform a lot of refactoring because you have to comply with your tool, you have to simplify the reasoning about some algorithms, or you want to remove some patterns that are harder to reason about. And so you're refactoring a lot. And in our project, we found some bugs already at that stage. And then once this was done, giving this code to Stainless allows it to generate a bunch of VCs automatically that would try to verify the termination, the absence of overflow, the inbound accesses, and it can also find counterexample at that stage. And this means that even there, you would get some guarantees, even if you haven't write any specification yet. And so the takeaway is that every step of the process is actually providing some valuable guarantees. And so to conclude, in this project, we added the new verified Scala backend to the ASN.1 SEC compiler that is used by ESA missions. And to do so, we re-implemented and verified the static runtime library, specifically the subset used by the packets we were analyzing, to be crash-free and invertible. And then we modified the code generator to generate proof alongside the Scala code to be able to also verify the crash-free property and the invertibility, specifically for the sequence encoding. And we hope that with this project, we were bringing better reliability in space communications. And so I'm thanking you for your attention, and I'm happy to take any questions.
Hey, thanks. That's great work. So this is in Scala. You have got arrays of bits. They are heap allocated. I guess it runs on a JVM.
Yeah.
Is this like good and efficient enough for to be run on a satellite?
So it won't be run on the satellite. The Scala backend is used for the ground control station, on which you don't really care about that kind of performance. So we have in Stainless a backend that would generate some C codes that could be embedded, but we didn't use that in this project. And so our Scala code is intended to use only on the ground control stations. Okay. And so yeah, the arrays are heap allocated, and you have an array of bytes and so on. But it's on the JVM, and it's supposed to run on the ground control stations computers.
Okay, got it. Thank you.
So how much can you extend this to something like a JSON or a protobuf format that people use very often for serialization, deserialization? I mean, they have a lot of bugs too, right?
Yeah, so that's a really good question. I'm not sure how much of this particular work we could reuse because everything seems so tailored to exactly this particular compiler and this format and everything. But what I would say is that we learned during this project that if we want to do this kind of work, we should start from scratch writing a verified serializers and deserializer for this particular formats and not try to verify an existing one, because I think the effort would be larger than starting from scratch. But this is an interesting point, and that's future work that we want to work on.
This is very cool stuff. Thank you very much.
Thank you.
You know, this kind of serializing, deserializing has been it's seen a fair. It's a really cool application for sort of fancy verification, right? Yeah. And I think there have been a bunch of projects. Like I think what is the Adams group has something called Narcissus, which was in Cork. You probably know about that one.
Yep.
And then the F-star people have done a lot of stuff with like packet protocol deserializing and so on.
Yeah.
So are there, have you looked at these other things? Are there some different kinds of constraints? I wonder, do the proofs sort of look similar in spirit, or are they very different? Can you say a little bit about that?
Yeah, so I explored a little bit the Everest project from the F-star people, and I would say the idea is more or less the same. So they are also generating the proof alongside the code at the end. When I looked at it, at least, the generated code they were producing was not, because here what we are saying, like if you give a message format, you would get one function that could encode and decode this particular format. And then you have all the sub-functions that are used by this main one, but you still have this. In the Everest project, from what I could see, they were giving functions to read part of the packets because that's what the application was about with HTTPS and so on. You don't necessarily want to read the entire bit stream at once, and so they were giving more functions to access some particular values within this thing. So the approach is a bit different, so they don't have this big wrapper function that would give you access to the entire message. But I would say the approach is similar. For the proof, I can't really say they look really different because the tools are different, and so that's mainly it. But I'm pretty sure that the core concepts about the proofs are similar.
Okay, so
Thank you.